Hello, everyone, and welcome to our live session for today, February 20th, 2025. My name is Matthew. I'm one of the behind the scenes folks. I'm one of the course staff from our online classes. I also do program development here. We are happy to have you here. We're glad that you could join us today. So, for those of you who are returning, welcome back. For those of you who are new, let me just go over the process of this real quickly. So I have everybody post your questions in the chat. I grab the questions from the chat and we just curate those so that we can make sure that they are at a level that's a beginner level and that everybody, as much as possible, gets a chance to ask questions. And we also jump around a bit to try and get a variety of topics so that we can, have a variety of different discussions during the chat today. So with that being said, you can please ask your question only once. I do see everything, and so if we skip your question, it's just because it was either covered previously or that it's not at a beginner level. But we will get to the questions as we have time. So, Chris, why don't you say hello and welcome to everyone, and then you like to get us started with a topic for discussion, and then that can sort of promote some questions that can come up in the chat. So let's get going with that. Chris, I'm going to have to pause you for just a second. For some reason, the lav mic is not working, and I'm trying to figure it out right now. So we're going to have to redo that. I'm really sorry. There we go. Okay, let's start over. So everybody, I apologize. There was a technical malfunction. Our software was not reading the microphone properly, but Chris is going to start over with his discussion. I apologize for that. Thank you,
Okay,
everyone, for your
welcome
understanding.
everyone. I'll jump right in. The topical comment up front, which is not particular to astronomy but general to science, deals with the funding uncertainty and cuts in the new Trump administration to science and to all the federal agencies. This is definitely impacting astronomy because most federal funding for astronomy comes through NASA and NSF, with another part from the Department of Energy and a little bit from the Department of Defense. And those agencies are taking some heavy cuts. At the moment, it's mostly probationary officials in the civil service ranks, but deeper cuts are likely to come. And I wrote an op-ed in The Conversation, an online periodical that covers all different topics, about what the case for federal funding of science is. The numbers are very simple. Since the Second World War in the United States, 85% of economic growth has been driven by science and technology. And that also corresponds to the time when the federal government decided to jump in and fund research through universities and research institutes and federal agencies like NASA and NSF. And it's led to vigorous economic growth, the creation of many jobs, and of course lots of new knowledge. So there's an irrefutable case to be made that even doing basic science has great returns into the economy and to growth. So it's a pretty slam dunk case. Unfortunately, this is the climate we live in, where the cuts are being made essentially indiscriminately on the premise that there's a lot of waste in these federal agencies. And so astronomers are bracing for what may be quite deep cuts to the funding sources. So it's very personal. We just put in an NSF proposal that's pretty much stalled now because they're not reviewing proposals, and their funding may go down mid-year or in the next fiscal year, the one would hope to apply for. So these are times of uncertainty and anxiety among scientists because a vibrant and extremely successful research enterprise, the best in the world in terms of Nobel Prizes and top ranked papers and so on, is under threat, basically. So it's not very good news to deliver up front, but I'll just put it out there.
All right, well, thank you for that kind of sobering introduction. We'll give people a chance to digest that and ask some questions related to that coming up. In the meantime, we will start with some of the questions that folks have posted already in the chat. Shayna, to start with, who's on with us live, asks, "Hello, Professor. Our sun is made up of plasma, which is ionized gas. Gases are not supposed to have edges. So how is it that we can determine the sun's diameter, and especially even though it's different at its poles and equators?"
So it's a good question. The sun does not have a sharp edge. It's not like a planet that has a surface. The sun appears to have a surface. It appears to have an edge. But that's just a function of the opacity of the plasma that the sun's made of. So the sun is indeed a plasma. The temperature at what we see to be the edge is about 5,700 Kelvin. And at that temperature, electrons are not attached to protons. So hydrogen is ionized, helium is ionized, and most of the other elements are very trace amounts. And so the phenomenon of opacity that leads to us seeing the sun having an edge is to do with the fact that free electrons will scatter photons or light very efficiently. And so in the plasma of the sun, the photons are bouncing around and not able to travel very far before they scatter off an electron. As the density goes down as you move outward in the sun, you eventually reach a point where, on average, a photon will not hit an electron and it will actually escape. And so the edge of the sun corresponds to a place where the density has gone down to the point where electron scattering doesn't happen. And so the photons travel freely, and they travel directly to the Earth and take 8 minutes to do so. And so we see that as the edge of the sun. But it's not a physical boundary, it's not a hard boundary, and it's not an absolutely thin boundary as well. There's some finite thickness to the photosphere of the sun. That's what that layer is called, the photosphere.
Thank you. The next question is from Terrence, who is on with us live. Good day, Professor. Are fast gamma ray bursts only produced by black holes, such as quasars? And actually, can you just talk a little bit about fast gamma ray bursts? Where do they come from, and are they only produced by black holes?
So gamma ray bursts are phenomena that were discovered more than half a century ago. In the 1960s, the first gamma ray satellites were launched, and they saw very high energy gamma ray events that they couldn't necessarily localize. And the angular resolution of early gamma ray telescopes was really poor. So you could see the energy from a gamma ray, but you couldn't identify a particular target or place that it came from. And that improved over time. And so it took a couple of decades for us to understand the origin of these gamma ray bursts. But basically, you see one a day with a gamma ray satellite. And we know they travel very far. They're very high luminosity. They can be seen a large way out through the universe. And so basically, somewhere in the universe, a gamma ray burst is going off pretty much every second. Now, they're not all one phenomena, because once people looked at hundreds of gamma ray bursts, they realized some of them were slow, some of them were fast. The light curves, or the curve of energy in gamma rays over time, had different variations. Certainly, the fast gamma ray bursts, which had enormous energy, seem to be needing some very high energy initiation event, and black holes are obvious choices, because either collisions of black holes, of course, are very energetic events, but they're also rare, perhaps too rare. Whereas black holes ingesting matter, or swallowing stars whole, and so on, or just having uneven, non-uniform astrophysics in their immediate environment, can generate a lot of particle acceleration up to gamma rays. So this is not a completely resolved issue, but it does seem that black holes are implicated in the fast gamma ray bursters. But also colliding neutron stars and black holes may be responsible for some gamma ray bursts.
Thank you. The next question is from Soy, who's on with us live, who asks, if humans ever find microbial life beyond Earth, What ethical considerations should we take into account when studying or interacting with it?
That's a good question, and there are protocols, and scientists are definitely worried about this issue of contamination or the ethics of how you deal with life in another situation on another planet. Since it's almost certain that the first detection of microbial life will occur by looking at the atmosphere of an exoplanet that's probably at a distance of 20 to 50 to 100 light years, it's not of great practical concern because this is remote sensing. We are not going to visit these worlds. No spacecraft can get there in any reasonable time. So it's just remote information. We are not interfering with, altering with the worlds at all. We're just observing them. And so we can diagnose whether there's microbial life there, but we don't have any impact on it. So I don't think there are any ethical concerns. The only ethical concern comes when we either send probes out there or try and bring back possible microbes from beyond the Earth. That isn't likely to happen in any foreseeable future outside the solar system because our space travel is too primitive. It's possible that it could happen inside the solar system, underground on Mars, or perhaps in the European Ocean, or inside Enceladus, or on Titan, perhaps. So there are solar system objects where there could be microbial life, and there are definitely ethical concerns, both in the sense of not altering those remote biological experiments by interfering with them, and second, and probably more profoundly, by not bringing back samples that might contaminate and lead to, for instance, worst case scenario, a contagion on Earth. So there are protocols in place, and so scientists are going to be very cautious when microbial life is first detected, especially if it's in the solar system.
Next question is from Wendy Traver, who sent an email asking, what is the state of the Russian space program under Putin, under the current administration?
Russia is a faded world power, faded in many senses. It's faded economically. It's faded in terms of its isolation because of its behavior during the Ukraine war. And it's faded as a scientific power too. Russia has suffered a brain drain of scientists that goes back decades. It goes back until the short-lived Russian democratic experiment after the fall of the Soviet Union under Yeltsin, and then the sort of decay of that experiment into corruption and oligarchy, and then the rise of Putin. So Russian science has been in retreat for a couple of decades now. The space program also in retreat. Now, Russia had a lot of infrastructure built up during the first part of the space race. But really, Russia is essentially getting by on 50, 60-year-old technology. The Soyuz spacecraft, the workhorse Russian spacecraft that goes to the International Space Station, or it at least did until Russia withdrew from that project, has been going for over half a century. It's a pretty reliable rocket, and spacecraft. It's only failed a couple of times. But they're not innovating. They're not developing new technologies. So they do have a heavy lift capability. They have spacecraft. They have a lot of accumulated experience in aerospace engineering and spacecraft engineering. They've not lost all their talent. But Russia is I would say, a pale shadow of the space power of the 1960s and 70s.
The next question is from Jay Rod, who's on with us live. Good afternoon, Professor. The media has announced that for next year, an asteroid will hit the Earth. Will it be possible to predict when and where this might happen? And can you talk a little bit about how we can get it so specifically if we can predict that?
Yeah, I think this is referring to the asteroid that I'm pretty sure is called 2024 YR2. So 2024 it was discovered, and it has a designation YR2. This is an asteroid that does have a finite probability of impact in the Earth. So its trajectory has been mapped. 2032 is one date when it could possibly intersect the Earth's orbit. The scientific community and astronomers are monitoring near-Earth objects, or near-Earth or Earth-crossing asteroids in particular. And this is one of them. So there are not that many. This is a fairly small object, but traveling at 100,000 miles an hour plus, it would pack a real punch and sort of take out a whole regional area of Europe or the United States or wherever it happened to hit. So it's definitely a concern. The probability of impact has been variously calculated as down around 1%, and that probability will change as the orbit is calculated more accurately. In almost every case when there's a potential impactor like this identified, as more computing power is put into determining the orbit and more observations, the honing in on the orbit and the fact that space is big and asteroids are small and the Earth's pretty small too means the odds of a collision are really low, and they usually go down when you calculate a better trajectory. So that's probably what's happening right now. People are improving the data to just be sure if this is really a threat or if it's just something that'll come close and maybe be visible in the nighttime sky, which would be exciting, but not cause any damage to the Earth.
The next question is from Lawrence K. Hi, Professor. Will the expansion rate of the universe ever exceed the speed of light? Is that concept even relevant when we're talking about the expansion of the universe? And how does that not violate special relativity?
Yes, if dark energy has the properties we think it does, where it doesn't vary over time or space, then the accelerating expansion of the universe will continue, which means it'll move apart faster and faster. And yes, if you project that into the future, there is a time, billions of years in the future, when any 2 points in space-time are expanding at faster than the speed of light. And that means the universe will become acausal. In other words, there will be parts of the universe with which we can no longer communicate because they are retreating from us at faster than the speed of light. Now that sounds like that's a violation of the laws of physics, but it isn't, because special relativity, which is Einstein's theory that talks about the speed of light as an absolute limit, is posited to work in inertial frames. Inertial frames are local frames of reference, solar system or terrestrial, where you can synchronize signals and transmit signals, and where the motions are subrelativistic, faster than the speed, slower than the speed of light. And in that case, the speed of light is an absolute limit. Cosmic expansion is governed by general relativity, and general relativity doesn't have a speed limit. So space-time expanding faster than light is not a problem because the theory of general relativity can accommodate it.
Excellent. Thank you. The next question is from Hernan Reyes, who sent an email about the Pandora mission. The Pandora satellite plans to help scientists better understand the atmospheres of exoplanets. By observing some 20 transiting exoplanets, and to do so 10 separate times, staring at them for 24 hours each time. Can you explain a little bit about how Pandora will achieve what it sets out to do and how it will help us in the search for habitable worlds?
Yes, Pandora is a NASA mission. It's a small NASA mission. We know NASA does multi-billion-dollar missions. James Webb is the most expensive ever. But this is a small-scale mission in the range of tens of millions of dollars. It's a small telescope. It's slightly less than a meter in diameter, made of aluminum, not glass, launched in a spacecraft. It just got its launch date and for later this year, and its launch vehicle is going to be a SpaceX launch vehicle. And it's going to spend a year looking at about 20 exoplanets that have been pre-selected to be terrestrial size, Earth-like planets that transit their stars. So they're already known to transit. So they create these transit dips as the planet crosses the face of the star. And this telescope is doing essentially scout work for much better later observations with a bigger telescope. So it's going to observe the transits in optical and infrared wavelengths, and having wavelength coverage is important for this. And it will observe the spectrum when the planet is in front of the star and the light from the star filters through the atmosphere, and then when it's not in front of the star. So you've got a subtraction experiment, and the difference between those two spectra give you the imprint of whatever's in the atmosphere of the planet. So it's a sort of looking through spectroscopy for chemical components of the atmospheres of these exoplanets, hoping to detect biomarkers, traces of life. Primarily oxygen, you'd want to see water vapor. Methane could be a biomarker. And Pandora can look for all these elements. An important part of the mission and why it's in space and why it's a precursor to deeper observations is sometimes you can be fooled, because sometimes the subtle spectral signatures can be confused with variations in the star itself. So the star that the planet crosses the face of is not a shining light source that doesn't vary. It's a star. It has spots and phases and imperfections and blemishes, and they vary over time. So an important part of Pandora is to map out those temporal variations in the star itself, so astronomers don't get confused by interpreting a spectral signature in the atmosphere of the planet to something that's actually due to variability in the star. That's a really important part of Pandora mission. And one of my colleagues, Daniel Impey, is one of the investigators on that mission, so University of Arizona has a very strong interest in it.
Thank you. The next question is from Terrence, and I'll divide it up into two questions. The first one is, does Jupiter have a solid core at the center of the planet?
So there's pretty good evidence, but it's indirect, that Jupiter does have a solid core. And it starts with theory. Our theory of planet formation in the solar system and elsewhere suggests that planets start with rocky cores and then they accrete their atmospheres. In the case of the inner terrestrial planets, we see the rocky material of Mercury, Venus, Earth, and Mars, and then pretty slender, or in the case of Mercury, absent atmospheres. The giant planets also seem to have started as rocky cores, and then they accreted hydrogen and helium envelopes in the outer part of the solar system where the temperatures were cool. And so the gravity of those cores could gradually accumulate material. So that's the theoretical and simulation expectation. The actual evidence for it is indirect, because we sent probes actually into the atmosphere of a couple of the planets, the giant planets, but we haven't tracked anything down to the surface. You lose communication with any spacecraft when it enters the plasma, the hot plasma of an upper atmosphere of a planet. But you can use magnetometer experiments and other experiments and instruments on orbiting spacecraft to infer the mass of the planet and show that even though it's a small fraction of the total mass, there does have to be a small rocky core, probably 5 to 10 Earth masses in the center of each of the giant planets, Jupiter, Saturn, Uranus, and Neptune.
The follow-up question is, what produces the intensity of the radiation belt of Jupiter, and why is it dangerous for satellites, machines, to travel through that area where Jupiter's moons are?
Right. Well, Jupiter is a huge planet, has a strong magnetic field, and magnetic fields can accelerate particles, especially a magnetic field of a giant planet, which is very strong and very extensive. And so there is a extended region around Jupiter induced by its magnetic field that is plasma, that's high energy plasma. And those high energy particles are intensely damaging to spacecraft that travel through them. So all the outer solar system missions, any of them that have gone in the vicinity of Jupiter, have had to be carefully aware of this. And you can navigate around it, but you actually have to have radiation hardened instruments on any mission that heads into the Jupiter system. Europa Clipper has had to worry about this, and there was a concern before Europa Clipper was launched recently that its electronics and its semiconductor chips were not sturdy enough to resist the intense radiation environment that they would find in the Jovian system. And they tried to strengthen it, they tried to insulate it more, buffer it more, but it's not really known if they solve that problem. So this is a very inhospitable environment for spacecraft.
The next question is from Lawrence, who's on with us live, who is referring back to your initial comments about science funding. Do you think that civilian entities will replace government funding, and can non-government funding replace any anticipated losses?
Right. So unfortunately, the federal role in funding research, especially pure research, is really strong. So the overall research and development funding in the United States has grown substantially over the last 30 or 40 years. But most of it now comes, 3/4 of it now comes from the private sector, from corporations and industry. And their contribution to the total R&D funding exceeded the federal amount about a decade ago. the federal amount has been stagnant or slightly falling, and the corporate amount has gone up. The problem is that corporate funding for science, research, and development goes to applications. It goes to things that companies can monetize, to products, to services, and it doesn't cover the kinds of astronomy that I do. It doesn't cover high energy physics. It doesn't cover certain kinds of fundamental research in other fields. So if you want to do fundamental research, you need federal funding because they're the only people who can do it. Philanthropy could play a role and does play a role, but again, philanthropic organizations often have very targeted needs or targeted giving. It's not always in the areas that scientists wanted research when they ask a blue sky question about nature. So federal funding is in that sense sort of irreplaceable. It's also worth noting, as I did the research for my op-ed, that you might think pure research or blue skies research is not very useful, but it turns out that the knowledge base created by pure research facilitates innovation. And so there are studies worldwide actually that have shown that pure research generates twice as much economic return as applied research. That almost sounds counterintuitive, but it's the case. So pure research has to be funded by the federal government. No other source can do that. It's less than 1% of the federal budget. So, you know, even if you cut it, you're not really saving much money. You're not solving the federal deficit problem. So to me, it's very short-sighted to cut the federal funding for science research.
The next question comes from Andy Horn, who's on with us live and asks, since you recorded the lectures for your online classes, what are some major astronomical discoveries that have been made that might not have been included or covered in those lectures?
I think the most rapid change in the subject has been in the area of exoplanets and astrobiology. We still haven't found life in the universe, so if life were found elsewhere, I would definitely be shooting some new lectures. So what's really changed is our knowledge of exoplanets, the number of them, the number that are habitable, the ideas of what drives habitability of planets, the range of properties of exoplanets that's been revealed by research in the last years. So that's the most rapidly growing field. In cosmology, there are issues that are on the surface and generating news headlines, but actually nothing fundamental has been resolved. We still don't know what dark matter is. We still don't know what dark energy is. The Hubble tension is an issue that's been around for a while. So that's maybe one thing where I would want to add or amend a lecture. But actually in cosmology, although it's a field of very active study, we haven't made a lot of fundamental progress lately. So it's really exoplanets and astrobiology where all the action has been lately.
Excellent. The next question, we've had a couple people ask, and just so the viewers, the people who are with us today know, we often get questions about career paths in astronomy, and I don't always pick them because we get asked that so often. So I try to limit it to every other or every few sessions. But it's been a while since we talked about this. If you have specific questions, feel free to go back to some of our old live sessions. And we talk extensively about how to get into astronomy and things to study. But we can do a brief review here. Ganga asks, can you talk a little bit about your educational journey, and how someone, gets into the field of astronomy through their schooling?
So I went through education mostly in the British system. I was at high school there and then undergraduate and a graduate student. And in general, not just Britain, but in Europe and the United States and other parts of the world, the base training of most professional astronomers was physics. Their undergraduate degree typically was physics. Sometimes physics and astronomy, sometimes physics and mathematics, sometimes just mathematics. But it was for sure a physical science, and in my case it was physics. Because astrophysics is just the application of physics into the universe, so it's a logical extension of what you might do in physics by picking one specialty. And then as a graduate student, whether it's PhD or master's, you home in on that aspect and take another set of courses that are particular applications of physics or astrophysics into the universe, as well as observational techniques, computational techniques, and so on. That's the typical training of a professional astronomer. So it's a base coat of paint, or a gateway drug, if you like, of physics leading to astronomy or astrophysics. It is less common, but can happen to move into astronomy from the life sciences, because astrobiology is a big field now, so that definitely is happening more than it used to. It's also possible to get into astronomy and astrophysics through engineering, mechanical, aerospace, various electrical engineering, and so on. There's quite a lot of extra physics and math you would need to take as an engineering student, but it's possible. So there are more than one career path or into being a professional astronomer, but I'd say the bulk, 2/3, 3/4 in my acquaintance, start the same way.
The next question is from Sonnet 786, who's on with us live. So maybe you can. So the question is, why is the universe flat and not otherwise? But perhaps you can talk a little bit about what flatness refers to in terms of the universe.
Right, so flatness refers to the shape of space-time. So the universe has three-dimensional space-time, or 3 dimensions of space and 1 of time, described by general relativity. And that space in general relativity can have curvature. The theory, because gravity and mass bends space, the theory allows for curvature of space-time. Locally is in the case of a black hole, and globally is in terms of the universe as a whole. And it's not clear until you do the experiment and make the observation what the curvature of our universe is. We've made these observations, and the microwave background observations have now shown with very great precision that the universe doesn't have any global curvature. The universe is flat, or flat space-time, within about 1%. It's very accurately flat. And then the question becomes why? Because if the universe started very small and dense, then its space-time must have initially been quite curved or quite compact. And the explanation for the flatness of space, as observed, is inflation, is the idea that the early universe had an exponential phase of expansion very early on, driven by fundamental physics of the unification of the 4 forces, or 3 of the 4 forces. And that smoothed out and flattened out space-time, which when it entered its more uniform or gradual rate of expansion, the Hubble expansion, continued. And so we observe space-time to be flat. These experiments have been done a number of different ways now, and they all give the same answer.
The next question is from Sammy, who sent an email asking, is it possible to see whether some of the long period or hyperbolic objects, such as comets, have had close encounters with planets that are far out in the solar system, or might give us a sense of if there's like a so-called planet X out there beyond Pluto's orbit?
So it's an interesting idea of whether we can use the outer solar system objects that are in elongated elliptical orbits like comets as test particles to probe interactions or the presence of other objects that we haven't yet discovered. So it's a good idea, and it's an idea in principle that will work. The problem is that these perturbations or these effects of a close encounter between a comet and, say, some hypothetical planet X in the outer solar system, since it's not going to be a very close encounter, it's going to be a subtle interaction that will deviate the orbit of the comet by a modest amount. The trouble is there are other things that can deviate the comet by a modest amount, other interactions with inner planets, or even the tidal gravity field of the system near the Milky Way, the system of stars that we're close to in the Milky Way. And so it's very hard to unpack it. Also, the orbit will repeat, and so you're having to do the forensics of looking back for an influence on the comet that may have happened thousands or hundreds of thousands of orbits ago, millions or hundreds of millions of years ago. And that's really too difficult to tease out. The data is simply not good enough, and the chaotic influences in the solar system are just too substantial to tease that out. So although it's a good idea, it's never been done to use a comet as a probe of a, say, hypothetical big planet in the outer solar system.
The next question is from Bina, who asks, can magnets work in space, and is it possible to use magnets to clear up our space junk?
I mean, both answers, yes. Magnets definitely work in space. A magnetized metal, including iron, nickel, cobalt, there's a number of metals that are magnetic. They continue to operate in space. So the magnetic domains that are trapped in the metal are not affected by the space environment or a vacuum. And so, yes, magnets can exist in space. In fact, you could think of the Earth as a giant magnet, or any planet with a magnetic field as a giant magnet as well. As for whether magnets could be used to deal with the space debris problem, interesting question. And yes, people have tried to game this out with engineering studies and so on. And it's in principle a good method, because the material out there, the metallic material out there, would respond to magnetic field. The trouble is it doesn't have a large range. Magnetism, strength of magnetism declines as the inverse square of the distance, just like electrical fields or light itself. And so once you're far from an object, the strength of the magnet and its magnetic attraction reduces very rapidly. So magnets, to clean up space debris, don't have a very large range. And also, to make a magnet powerful enough to pull in space debris, the magnet itself would have to be massive and huge, and therefore would cost an enormous amount to launch. So that's a second problem. And I think for both of these reasons, magnets are not seen as a viable option for dealing with the space debris. A sort of magnetic net is another possibility. That's a related concept. And that's where you use magnetic material, but you build it into a very large net. And so that gives you a larger aerial reach for your experiment. And people are investigating that idea right now.
The next question is similar and related, is from JS, who's on with us live. Does a compass work on all planets?
Well, a compass will work if there's a magnetic field. So compass obviously works well on the Earth. That's where they were invented. It would work on a planet with magnetic field like the Earth's. A compass would do you no use at all on the Moon because it has no magnetic field. And it would be of moderate use on Mars, which has weak, almost absent magnetic field. So compass is only as useful as the strength of the magnetic field of the object. Now, most planets we expect in the universe that are as massive as the Earth are going to have magnetic fields. So generally, for most planets that we might find out there, a compass is going to be a useful object.
The next question is from Old Princes, who's on with us live, and asks, how do scientists estimate the density of the universe? What methods and observations are used to calculate it?
So the way the scientists calculate the density of the universe is by looking at the change in the expansion rate, because the change in the expansion rate of the universe is governed by the material content of the universe. Now, we've seen in observations in the last few decades that the expansion rate of the universe is increasing, it's accelerating due to dark energy. And dark energy is not a material entity, so that's not really helping you with this calculation. But once you've accommodated or accounted for the effect of dark energy, then the rest of the mass of the universe is also altering the expansion rate, and in the sense of slowing it down over time as the matter pulls on other matter nearby. And so that changing expansion rate of the universe is the method that is used traditionally to estimate the density of the universe. And the number you get is that the density of the universe falls far short of being sufficient to close the universe and cause it to recollapse. And in that sense, the universe is geometrically open and would expand forever. And that's been accentuated by dark energy, which makes that an emphatic conclusion.
The next question, there are two related questions about Mars. Niad asks, do you think we will ever conquer Mars into a suitable environment? And Yazan asks, do you see a Mars landing happening soon? What are some of the biggest challenges? Are they technological, funding, geopolitical?
I think conquering Mars, as a euphemism, will take in this situation to mean terraforming, which is making it habitable by humans without having to live in a pressurized, sealed environment. I don't think we'll ever do that. Not that it's impossible physically, but that the cost and the time to do it would just be so enormous that I don't think we could ever feasibly manage it. So it is possible if you could somehow raise the temperature of the surface of Mars, you would start liberating liquid water, carbon dioxide, which would lead to a greenhouse effect, a runaway greenhouse effect, and you'd reverse the fact that Mars lost its atmosphere. You start to build up an atmosphere and trap heat, and then get to a point where the surface was habitable. But the enterprise of doing that involves enormous amounts of energy and an enormous amount of time. It's a very difficult thing to do. So no, I don't really think we're going to do that in any foreseeable future. The impediments to a human mission to Mars are substantial, and it starts with the orbits. There's a Mars launch window about every 17 months, because Mars and the Earth, of course, have different orbital periods, so you have to wait until the planets are aligned to do your launch. But it's not as simple as the two planets being aligned and one inside the other in their orbit, because they're moving in their orbit. So you have to play out, you're aiming your spacecraft for where Mars will be when you get there in about 7 months. And so the most energy efficient orbital transition between Earth and Mars takes about 7 or 8 or maybe 9 months, and only the window to do that only occurs every 17 months. So those are your primary constraints. The energy cost is still enormous, so the amount of material you'd have to launch to Mars is enormous. So added up, you have 7 months minimum to get there. You've got to wait 17 months to come back to your next launch window, and then 7 more months. So that's 31 months. So you're already looking at a 2.5-year mission. And however many people you send, to say 2 or 3, the minimum crew, you have to send enough supplies for them to live for 2.5 years. There's no infrastructure on Mars. There's nothing there. And if you were going to set up the infrastructure, that's yet more mass you have to bring. So it adds cost and expense and difficulty to the mission. So when you put these things together, you realize that it's an enormously difficult undertaking just to send a couple of people to Mars, to not stay very long, because they just stay for the minimum amount of time before they could come back in the next launch window. It almost doesn't make sense to send people 7 months there, let them spend a week on the surface, and then 7 months back in the same launch window. That really doesn't help you very much. It doesn't do much about learning how Mars works or setting yourself up for future habitation. So this is an extremely difficult experiment. And Elon Musk, in his pronouncements on Mars, has been very glib about that. He does have a Starship rocket, which in principle is capable of doing this kind of work, but he would need dozens of operational Starships to be able to do any simple Mars mission. Starship has had a few test launches, 6 or 7, some successful, some failed, but it's never launched from the surface of another planet, and there's no launch capability there. It would have to launch directly from the surface, which is not what Starships do on the Earth. So there's an enormous number of unknowns about Starship as well, if that's the vehicle we would use.
The next question is from Nahom, who asks kind of a follow-up question to the earlier discussion about the asteroid that we talked about earlier, that has a small possibility of impacting Earth. In a worst-case scenario, if this asteroid is found to be on a collision course, can something like a DART mission save us? Is there any way to deflect or redirect it? How early does something like that have to be done, and when is it too late?
I think it's good news. It's not a doomsday scenario. Yes, the DART mission, double asteroid redirect mission of NASA, was a very nice demonstration of a proof of concept of how you could change the trajectory of an asteroid or the orbit of an asteroid. It was done on a pair of asteroids that were orbiting each other, but by impacting one of them, but it proved the concept. And so yes, we would have enough warning. We would be clear enough on the impact months ahead, possibly over a year ahead, and that's actually plenty of time to launch a rocket and do a redirect mission. You don't actually want to destroy the asteroid, just blow it up, because then all the pieces would still be on the same trajectory and they'd still come and hit you as smaller pieces, still doing significant damage, although some would burn up in the atmosphere. So I think, yes, the redirect mission suggests a way we could deal with an impact, because we would have enough time to launch such a mission and do the deflection. And obviously the more time you have to plan this, the easier it is to do, because the amount of deflection you'd have to do on a trajectory goes down if you can catch it further away.
Excellent. Thank you very much. The next question is from David, who asks, what are possible changes in the moon? I guess, future, sorry, I am reading this question too much in real time. Can you talk a little bit about the viability and sense behind sending missions to the moon? Is that a good use of resources? Is that a good stepping stone for Mars? What are the benefits and challenges with going on a moon lunar missions?
So the moon is a natural stepping stone to further exploration of the solar system because it's by far the closest object. It's just 250,000 miles away. Mars is 30 to 50 million miles away at its closest approach. So it's a huge difference. And so as a stepping stone to Mars, it makes sense. And so the Earth, Moon, and Mars concept, which goes back a few decades, was based on going to the moon to prepare you to go to Mars. It also could prepare you on how you live on a barren surface of a planet with very little atmosphere and very little natural resources. The Artemis project with NASA is the attempt to do the transition from the Earth to the moon. Artemis has had a launch and is going to supposedly put astronauts on the moon, probably not for 2 more years, as a stepping stone to get to Mars. But it's using the Space Launch System, which has proved to be extraordinarily expensive, and so it's not clear if Artemis will survive the current administration's budget cutting. But generally, it is a sensible stepping stone. The Chinese, for example, who've landed successfully on the moon multiple times and have their own space station, they have a pretty advanced project to develop a moon base. So the Europeans have designs for this, NASA has designs for this, and the Chinese do. And with the current economic climate and technical climate, it's probably best to put your money on Chinese doing it first. And they also will use it as a staging ground for getting to Mars.
The next question is from Tuki, who's on with us live, and asks, I've heard theories about, possibilities of life on gas planets, sort of like big jellyfish floating in the atmosphere. These ideas are kind of old, but do they still stand up today?
Yes, there was a famous paper, to most astronomers it's one of those iconic papers you always learn about when you're studying the subject. It was about gas bags in the Jovian atmosphere. I don't remember the technical title. It was published in a highly reputed peer-reviewed journal. So it was, while it was speculative, it was considered scientific enough to pass peer review. And it was written by Carl Sagan, who's famous as a great astronomer as well and planetary scientist, as well as a popularizer of astronomy, and Ed Salpeter, one of his colleagues at Cornell University. So the Sagan-Salpeter paper hypothesized giant buoyant organisms, gas bags if you like, that live in an ecosystem at the temperate layers of the Jovian atmosphere. So Jupiter is far from the sun. It's the outer layers of the atmosphere extremely cold, but the inner part, due to compression and pressure and density, is actually very hot. So there's a temperate layer, and they just imagined an ecosystem of circulating buoyant creatures, predators and prey, an entire ecosystem that could exist in this temperate mid-latitude zone of the Jovian atmosphere. So it was a proof of concept. It was kind of a provocative speculation. And whether people take it seriously now, half a century after that paper was written, I'm not sure. I think the odds of life in the Jovian atmosphere are very low, because it's also the question of how do you get there? How do you actually form life? We think we know how life started on the Earth. It almost certainly happened in a liquid environment with local energy sources. And doing life from scratch in a gaseous environment is extremely challenging, and really nobody knows how that would work.
Excellent. Thank you very much. The next question is from Tony White, who asks, will it ever be possible to see an exoplanet up close with a future telescope?
If we're talking about the next generation but one, then yes. So exoplanets are far enough away. Even the nearest exoplanet, if it were approximate 10 Centauri's exoplanet, are tens of trillions of miles away. So they are Earth-sized planet at that distance is impossibly small for any telescope to resolve. So you really need both a space telescope of enormous aperture or ground-based interferometer, optical interferometer, also of enormous baseline and aperture. And none of these facilities are available to us now. So seeing even the nearest exoplanet in any kind of detail, maybe even at the level of 10 pixels across the image as opposed to a single pixel, is decades away. It's a very challenging experiment.
Now, the next question is from Daniel, who asks, do you think that internet from space can or will take over from ground systems based on all of these satellites whizzing around the Earth, and what effect will that have on astronomy?
There are advanced plans to develop an internet in space to have, because eventually, as the solar system gets populated by more spacecraft and eventually humans visiting various different destinations, you're going to need ways to communicate. It's really augmenting, though, what we have on Earth, because the challenges of internet in space are enormous. They're mostly the latency caused by the long travel times, even at the speed of light. It takes a substantial amount of time to travel between destinations, so you have a long latency of communication, which is something you just don't worry about on the Earth. And then you have bandwidth issues, because the amount of computational power you can put up there, you can have great server farms or huge supercomputers, is modest. So internet in space will serve a purpose and is being imagined. Bennett Cerf, one of the founders of the original internet, now in his 80s, I think, is working hard on interplanetary internet as his final act as a researcher, I guess. So there are plans on how to do it, but it would be independent of terrestrial internet, because terrestrial internet doesn't have the problem of latency, but it does have the problem of enormous volume of communication. So the bandwidth requirement is really high. Extraterrestrial internet will always have a relatively modest bandwidth, so there'll be a limit to how many signals you can send backwards and forwards.
The next question is from Wendy, who would like to know, what would the implications be if the speed of light varied even slightly over time?
It's an interesting hypothetical, and actually astronomers have tried to do experiments to probe whether the speed of light is a variable, whether it varies with direction in the sky you look, and that's never been seen, or over distance and look back time in the universe. And there's been controversy there, because a few papers over the years have claimed to indirectly detect variation in the speed of light over time in the universe, and others have not found that effect. The implication would be substantial, because there's no physics to explain a variable speed of light. The physics of the speed of light is defined by special relativity, and special relativity has that as an absolute constant, it's a constant of nature. So there's no mechanism in current physics for the speed of light to vary, so it would represent new physics.
All right, it is now 10:58. I think we probably have time for one more question before we wrap up today. So the last one that we're going to take is from Kumar's, who sent an email. How far are we from fully understanding the mechanisms of galaxy formation, and what are the key unknown principles which remain to be discovered or understood?
Galaxy formation theory is progressing steadily. The first ideas of galaxy formation theory go back to the 60s and 70s. People like Donald Lyndon Bell working at Cambridge and others. And these ideas have progressed as we learn more about dark matter, because galaxy formation is mediated by what the nature of dark matter is, since dark matter dominates normal matter by a factor of 5 or 6. So that unknown, that uncertainty about dark matter and its fundamental nature, is one of the limiting factors on maturing galaxy formation theory. So that's one issue. And then the second issue is the role of black holes. Since every galaxy we think has a black hole, and the black holes have been growing very rapidly since early in the universe, galaxy formation is also a question of how black holes form. Whether does the seed black hole form first and then the galaxy accrete around it, or does the infant galaxy, small galaxy, before mergers grow it, form first and then the black hole forms within that. It makes somewhat different predictions of what we would see in the everyday universe, in the current universe. So those are the two areas, black holes and dark matter, where galaxy formation theory is kind of stalled or stuck because we need some new insights, new physical insights to make progress. Great questions as always, thank you. Matthew and I will get together soon and figure out our next few dates, but we look forward to seeing you in a few weeks.
Excellent. Thank you so much for joining us. The next session, the next live session we have on the schedule is for 2 weeks from now. I believe that is March 6th, I think. So it's 2 weeks on Thursday. And if you are on our mailing lists for our classes, then we will send out the announcements. If you are not on those mailing lists, then scroll back to the top of the chat. I put a link in there so that you can join our Google group, which is a listserv where we send out announcements and reminders about upcoming live sessions. So again, thank you so much for joining us today. I've posted links to our classes in the chat, as well as some articles that Professor Impey has written recently about science funding and plans for Mars exploration. Please check those out, and we'll see you again in a couple of weeks. Take care, everyone.